Hey, so welcome to High Stakes Mathematics. The situation is, it's a sci-fi scenario. You have to kind of imagine like a sci-fi short story, okay? And aliens come to Earth and they immediately destroy a city just to kind of prove to you that they're serious. And then after doing that, they say, right, we're going to put each of the cities of the world on the chopping block. And there's quite a lot of cities in the world. There's like 1,000, probably 1,000 quite big cities. And unless you can answer a basic maths question, we will destroy the world. Well, we'll destroy this city. And people might be shocked. And they might ask them, like, why are you doing this? And like, refuse to answer that. It's a sci-fi scenario. That's all that counts. And so they say, okay, well, what are the problems? And they say, well, we're going to use Wolfram problem generator, which is like this abstract problem generator that's made by Wolfram. I don't know what it's called, like Wolfram Studios or something. And it covers basically like all of high school mathematics. So you can get arithmetic, number theory, algebra, calculus, linear algebra, statistics. Like they've got all these different things that you can pick from. And they start off and they say, right, we are going to destroy another city unless you can tell us what 5 plus 4 is, right? And you might think, okay, well, that's a really dumb question. That's like incredibly easy. Like, why would we care about why would we put so much effort into that? Anyone could answer that. But I think it's really interesting because I think if you really did have a whole city on the line, if they really were going to destroy an entire city, if you got this problem wrong, you'd want to be like really, really sure that you're correct. And like, okay, 5 plus 4 equals something is a really easy question. But what if they brought up the question, here's an advanced question from the trigonometric substitution thing. This is high school maths, but like, are you sure you can do this integral so well that if you miss a minus sign or if you miss like a factor of a half or something, they're going to destroy an entire city? Like, how confident are you in your answer, right? And I mean, maybe there's like a shortcut where if you use like Wolfram Alpha problem solver to solve the problem that Wolfram problem generator has created, then you're almost certainly going to be marked correct. Because if there is a mistake inside its system, it's probably got a mistake in the problem generator as well as in the solver. And so it might cancel itself out. But again, you can't really be sure of that, right? And maybe the aliens are asking these questions, but they're not marking them using Wolfram generator. They're marking them using their own alien systems. Okay, so what are we going to do? Like, how do you get all the mathematicians in the world, and they're all like super serious and they're committed to this? Like, how are we going to solve these like really like quite straightforward maths problems, but in a way that we're definitely sure that we're correct? And it would be interesting at that point to ask the aliens, like, what is mathematics? Like, what do you mean when they say that? And they might say, okay, it's Zermelo-Fraenkel set theory with the axiom of choice and its consequences. And now that's quite a complicated thing, which I might go into later in a future video. But we would say, in response to that, oh, that's very coincidental. That's often how we think about mathematics too. And they go, oh, really? And it's like, yeah, we think about mathematics in almost exactly the same way with the same names for the people who invented it. That's a really bizarre coincidence. And so wouldn't it be great if we had a giant database of proofs where from the 18 really basic Zermelo-Fraenkel set theory axioms, we could have all of the consequences of those all logically proved out in a really nice way, and then we could look up the answers to some of these questions in the database, right? And we'd know that it was correct. And here we arrive at Metamath, right? So Metamath is a system where, well, Metamath itself is an abstract proof system where you can pretty much prove anything you want based on a lot of different logics. And then set.mm is a giant repository of Zermelo-Fraenkel set theory, like results. Okay, so for example, in this giant database, there's about 40,000, there's a theorem list here, and there's about 40,000 things that have been proved. So it starts out with like the set theory basics, and like it starts out with first order logic, like it's just like, what is logic and how do you axiomatize that? Then it has set theory, and then it takes a long time, it takes all to part 5 until you start defining what numbers are. So it's got real and complex numbers, it's got a bit of number theory, it goes up to sort of a middling undergraduate level, maybe an advanced undergraduate level. So it's got some stuff about algebraic structures, vector spaces are in there, that's one of the most famous things in maths. Bit of linear algebra, useful topology, analysis, functions, graph theory. It's got various different things built up, about 40,000 proofs. And one of them, for instance, is 2 plus 2 equals 4. So it has proved in the database 2 plus 2 equals 4. And this is the proof. And that's incredibly useful. And moreover, everything in this proof is either an axiom or it is a definition, which is kind of arbitrary. I mean, you could relabel the number 4 with some other letter or number and rename it Catra or something, and you could do that throughout the entire database and it wouldn't really change anything. So definitions are much more to do with how you label things than they are to do with the actual structure itself. So it's either an axiom or a definition, or it's proved from one of those two things. So when it says, like, this adassi is a step that it's used in this proof, right? That is about the associative law for addition. So you're allowed to use this associative law. And the way Metamath works is it's about substituting things in slots. So you substitute in, if you have A, B, and C are all complex numbers, you can substitute them in. So you have A plus B plus C equals A plus B plus C, right? So it's a slot-based thing. And what they've done here is they've had 2 plus 1 equals 2 plus 1 plus 1, right? And you know that that's correct because it's used these lines 6 and 7, right? 2 is a complex number, 1 is a complex number, 2 is a complex number, and it's put them in like this, right? And so you can say, okay, but what about ADASI? Why do we trust that? Well, that has its own proof, right? Which is then proved from these two things. So it's got some axioms and it's got some assumptions. And then it's saying, okay, well, if we assume that this ADAS is true, then we can use this logical consequence to put them together. And you say, okay, but what about MP3AN? Why do I trust that? Well, you can click on that, and that takes you down to a lower level. So this is now talking about logic because it's using phis and psis and chis. And it says if you have 3 things which are all true, then if you assume that these 3 things all being true implies this, then if each of those 3 things is true, then that thing is true. It's not that complicated. If A and B and C implies D, and A, B, and C are all true, then you get D, right? And you say, oh, but I'm not sure if I trust that. Well, maybe these are the things that have been used in this proof. Okay, so we'll look at MP2AN, and we'll keep mining our way down. And then here is quite a cool moment where you see the first example of an axiom being used. So this axiom MP, this is axiom of modus ponens, which is one of the most basic building blocks. And so basically, if you take any proof in a database and you mine it down far enough, you end up back at the axioms again. So this is just done, there's no proof because it's done this is assumed to be true without any proof. You have to start with some set of axioms. And this is one of them, modus ponens, which is very famous. It says, if phi is true, and phi implies psi, then psi is true. And that just seems sort of beneath the level at which you could kind of prove it. It's sort of such a basic idea of, if phi is true, then psi is true, and phi is true, therefore psi is true. Okay? And you can do that any way you like to go in the tree. So if we go back to 2 plus 2 equals 4, we can look at ovec2i, for instance, and we can say, well, what's that based on? And that actually uses one of the axioms directly, which is interesting, and it also uses ovec2, and we could dive down into there. And it actually tells you at the bottom of the page, it's quite interesting, and it says it's proved from these axioms, so it shows you which are the different axioms that it's used. There's about 18 in total, I think. And it depends on these definitions, so there's various different things that have been defined somewhere in this tree beneath that. And it's referenced by, and this thing is so popular, it's been used in, and you can see how many theorems are on the database. This one's number 43,096. But all of these theorems use this somewhere in their proof. So for example, let's just pick a random one. Pythagorean, what's this? So it's a lemma for a thing called Pythagorean triples. But yeah, somewhere in here, it will use what we were just looking at. Was it ovec 2? That's ovec 1D. It's different. Yeah, ovec 1, 2D. But this is a serious proof. 120 lines of proof. I mean, look at that. It's just a crazy web of symbols, right? So a huge amount of work has gone into this database, which is really cool. Okay, and this is actually quite a cool theorem. I quite like it because it's if A equals B, then if you do something to A, so long as you do the same thing to B, then it's still equal, right? So if I have 5 equals 5, and then I say, 5 equals 3 plus 2, then I can say 2 plus 5 is equal to 2 plus 3 plus 2. It's allows you to kind of build up expressions more broadly, which is quite cool. So for example, in this proof, where's that been used? So yeah, it's been used here. So if you have 2 equals 1 plus 1, then if we add 2 to the left and we add 2 to the right, the results are still equal. And that's justified by this ovec2i, which is justified by an axiom and ovec2. And then ovec2 is justified by a couple of definitions and then various other things. And you can keep mining it down all the way until eventually you'll hit some axioms. So ali's really basic. Yeah, so ali.1 is based on just 2 axioms, axiom 1 and axiom MP. And so yeah, that's really low down in the tree. And you can kind of tell because it depends on very few axioms and then is just referenced by a gargantuan amount of things. It's really basic logical machinery, which is really cool. Okay, so the Metamath database is a really cool place just to mess around. It's really fun. Okay, so this is my suggestion then for how to save the planet from alien invasion, like that we're going to get our cities blown up if we start making mathematical mistakes, is what we'll do is we'll take the questions from the problem generator and then we'll prove them using Metamath, and we'll get a machine-generated proof, which is checkable by machine, and then we'll hope that it's correct. And you can ask the question, well, why should we trust the machine-generated proof, like more, say, than a human-generated proof? And like, one of the things with it is the way Metamath works, and I can talk about this more in a future episode if that's interesting, is that it works a lot on substitution. So really all it's saying is, this ovec2i, for instance, it just has slots for substitution. And it says, if you accept that this is true, then you can use it so long as you substitute in correctly into this expression. And that's a very simple idea, and that's the whole basis of the database. And so the database itself has been checked by a lot of people, but it's also got like about 8 or more independent verifiers written in different languages, which are run on different hardware. So it's a really powerful thing to be able to take a maths proof and encode it in such a way that a computer can check it. Because then you can run it in lots of different ways. Like this whole database gets checked every time you start up your proof environment. It will check the whole database for you. In fact, if I show you this, when it loaded up MMJ2, which is the environment, like the proof environment I'm going to use to prove things, it actually verified all the proofs in the database, all 40,000 of them or something. So it went through and did that. And it did that on my machine. This is the proof environment, MMJ2. And it did that on my machine, on my hardware, using this instantiation. But there's lots of other verifiers which are run on different people's machines, and some are on Windows, some are on Mac. So it's very unlikely there's an implementation mistake in all of those implementations. So if you agree with the basic way that Metamath is organized, which is organized in a very simple way, then you should expect that all the proofs that are checkable are okay. So hopefully this gives us a real sense of solidity that these things really are okay. Okay, so we'll be able to tell the aliens exactly what we think. So, okay, so if we start with the first question, 5 plus 4, right? If I look in the database, I say file, get proof, 5 plus 4 equals 9. I think it's going to be equal to 9. And this is like Metamath notation for how theorems are labeled in the database. And you kind of get used to it after a while, but it's, you know, P is for plus and E is for equal. So let's see. I don't want to save my changes. Okay, so it found it. So it said, and if I press Control U, which is for verify, it will then generate the proof for me. So it's saying this already exists in the database. It was done by Norm McGill in 11th of May 2004, so quite a long time ago now. And this is the proof. And it proves in the end that 5 plus 4 equals 9. Okay, great. So we're done. Like, we are sure, if you trust Metamath, if you trust the computers it's run on, and you trust the Zermelo-Fankel set theory axioms, which the aliens were very kind to verify that's what they wanted us to prove things in, then you can be pretty sure that 5 plus 4 equals 9. So if we go in here and we put in 9, then the spinning wheel of doom says it's correct. Okay, so we didn't get a city destroyed this time, which is good. So that is an advantage. Okay, 7 plus 4. Let's try that. So let's see if that exists. 7 plus 4 equals 9. No, that's not going to exist, right? Because I've messed up the problem. See, good thing I'm doing the checking, because if I'd have just written that in straight away, we'd have lost the whole city. That would have been a really bad example. Okay, so again, back in 2015, Mario Canero proved it. 7 plus 4 equals 11. And this is how larger numbers larger than 10 are written in Metamath. I'll go through that in a minute. And so that's been proven. Okay, so we can do this. So we can say, okay, we're sure that this is proven. Right. So the aliens say, okay, you can do your basic addition. Okay, fine. Well, maybe we won't destroy you then. But can you do advanced addition, right? So what about 298 plus 193? Okay. And let's see if that's in the database. So file, get proof. 298 plus, what was it? 298 plus 193 equals, now I have to know what it is. I think that's 300, 480, 491. Is that right? Let's see. Okay, no, didn't find it. Okay, and let me just check. Let's see what Google says about. Okay, yes, Google agrees it's 491, right? So that isn't in there. And one reason you can kind of tell that isn't in there is because there's 40,000 proofs in the database. So they've done all the numbers up to 10 of like, 2 plus 5 and 6 plus 7 and so forth. But actually, you need to do about 50 proofs to get all of those in because that's how many there are. And if you did all the numbers up to 100, you'd need like 5,000 proofs, because you've got to do 23 plus 76, and you've got to do, 84 plus 19 and 12 plus 38. And you've got all of these different combinations. And so actually, as the numbers get bigger, the number of proofs you need are huge. And so if you wanted to do if you wanted to have an individual proof for everything up to 1,000,000 plus 1,000,000, you would have like 1 trillion proofs. And so obviously that's scaling like n squared, which is no good, because it's just going to blow up out of control. So what we've got to do is, for each of these larger ones, we're going to have to prove it ourselves. But there is machinery inside the database for helping us do that, which is good. Okay. So let's see if we can do 298 plus 193. So we'll do a new proof. Here we go. First time we're doing this. Theorem label, just give it a bit of keyboard mash for that. And, right. Okay. So let's see if we can prove something. So what are we trying to prove? We are trying to prove that 293 plus 298. I'm going to destroy the earth with typos. 293 plus 193 equals, okay, and Google said it was 491, right? Okay. 491. So let's verify that. Okay, so it says no typos, which is good. And one thing that's quite interesting to see is like why am I writing all these semicolons in? So I think it's def, or is it def? Let me search for that. I'm trying to find the theorem for which it shows you why it's defined like this. But basically, it's quite clever. Each colon represents multiply by 10. So when you're writing the number 491, really you're only dealing with the integer digits up to 10. So you're dealing with 1, 4, and 9. But it's saying it's 1 plus 10 times 9 plus 100 times 4, right? And that's what gives you 491. And so then the theorems that deal with it all deal with how to add using these things. Okay, so for instance, I think what we want is dec add. Yeah. So when it comes up in blue like that, that means I've got the name of it right. So if I press Control U, it will pull out from the database. And so what it's saying is it knows how to do decimal addition, right? And it's got all these prerequisites. So you need to fill 8 of these things in. It's got all these slots that need to be filled in. But if you fill all those incorrectly, then this is true. Okay, so this is how the database works. It's all substitution, right? So let's fill it in. So this I want to be 298. And then when I fill that in, it also fills in this slot, because some of the, like C2 appears here and C2 appears here. So once I fill it in, it will appear there. And then I want this 193 to be there. And then this is a little bit more complicated because it's got like a comma, or it's got a semicolon already in front of it. So it's looking for me to break this down into smaller amounts. So I could have C5, let's try that to be 49. Colon 49, and then C6 will have that to be 1. Okay, so now it's filled in quite a lot of this, but it's still doing the same thing. It's trying to break down these numbers into smaller pieces. And so if we... I am not sure if this is going to work, because we may get into trouble with carries. I think we're going to need something that has carry, but let's see. We fill that in, and then we take this 193 from this side over here to fill these two in. Okay. So yes, okay, so this is interesting. So when it's got blue marks next to it, that means that it's found something in the database to tag onto. So 2 is a natural number. If n and 0 is natural numbers excluding 0, so counting numbers. And you can see that the definition of this is called 2nn0, and it defines that. So it's found it in the database. So it's found all these, and it's also saying, okay, well, if I have these two, then this decal, what that does is it says if you have 2 and 9 are natural counting numbers, then colon 29, so that's 29, is a counting number 2. So that's pretty useful, 81. But something's gone a bit wrong, right? And what's gone wrong is that D18, 9 plus 9 is 19. I think you're going to struggle to prove that. unfortunately. And then also D8, 8 plus 3 equals 1. And so what's happening is 8 plus 3 is really 11, right? And that's because we need a carry. So when we add the 8 and the 3, we need a carry. So I don't think it's dec add. I think it's dec add C we needed to use in the beginning. And that should help. Okay, so we're going to go back. Can delete this. They really shouldn't have picked me when the whole world was on the line. Okay, so let's get rid of that. Let's see if this works. Dec add C. Okay, so now it has a carry of a 1. And let's see if that works. This is kind of how Metamath works, is you just got to kind of play around with it and try and get it to do what you want. And just kind of, yeah, see what happens. Okay. Put that in there. How are we doing? Is it doing anything too crazy? No, I think that's okay. And then I use exclamation mark. An exclamation mark is really useful because it lets you, it's telling the MMJ2 to say, if you can find a way of doing this for me, search the database, see if there's any way I can link these together. And fortunately, because this thing was exactly the same as the line above, it actually deleted it and moved it one higher up. And it says it's proved it, which is great. So format complete, Metamath proof generated. So it's generated this proof for me. This is its encoded way of saying what the proof is. It relies on all of these different statements. So we can see we've said 2 is a natural number, 9 is a natural number, and then 29 is, 8 and 1 is 9, and then we have 19 because we had a 9 from here and a 1 from here. I don't know, I wonder if we use this D2 anywhere. That's an interesting question. I think if oh no, it does use it down here. That's interesting. And interestingly, it's used this dec suck. So this is the successor. So it's saying 4 and 8 are natural numbers. 8 plus 1 is 9. 29 plus 19 is 48. Therefore, 29 plus 19 plus 1 is 49. So it's saying if these 4 things are true, then this 4th thing is true. Which is really interesting. Okay, and it's filled it all in the blue. So blue means success. So the Metamath database agrees that it is now proven that 298 plus 193 is 491. So if we put 491 in here, I don't typo Rio de Janeiro out of existence. Correct. Okay, that's great. So there we go. So that is basically how addition works and how to prove adding up large numbers in Metamath. And you can see that because I started with these relatively these special numbers, you could pretty much put any numbers in here that you wanted. If it gets really large, it's more difficult because you have to have more carries going back through the system, and that gets a bit more complicated. But generally, addition, not so bad. Okay, so arithmetic, that's going pretty well. So let's see what other monstrosities I might have. So then maybe if we can add, can we subtract? Can we multiply? Can we divide? And then those are just kind of a mixture of problems. These 3 categories are a mixture of problems of the 4 above. And then fractions. But yeah, then after that, there's all kinds of fun stuff to worry about, like number theory, greatest common divisors. I mean, can you prove the least common multiple of 2 numbers? Can you prove primality? Can you prove, really genuinely from the set theory axioms all the way up, so it's computer verified? Talk about integers, rationals, calculus, derivatives, quotient rule, U substitution. These are all matrices, determinants of matrices, vectors, etc. Statistics. I don't know if there's any statistics in the Metamath database. We may end up having the Earth completely destroyed because they didn't bother to implement statistics in Metamath. I say haven't bothered. They're working really, really hard on it, and it's really impressive what they've managed to implement so far. So, yeah, there we go. The world is safe for another day because we managed to solve that one problem. What did we do? Oh, I think I cleared it. Yeah, there we go. So I did 5 plus 4, 7 plus, I did 7 plus 4 and 5 plus 4, and I did this. And so they said, all right, we'll spare 3 cities. So that is exciting. So hopefully in the next episode, I'll be doing less explaining and I'll be able to do a bit more proving, and we can kind of carry on with exploring it. So I hope you've had fun. Hope you've enjoyed this high stakes mathematics with Wolfram Problem Generator and Metamath. And hopefully I'll see you in the next episode.